Okay, today we study X21NQ. You can download the file, the PDF file of this lecture from kpop.org, and at the table of contents you can click X series to reach X21N. Click this to find X21NQ. And if you click this, you will find the recorded version of this lecture later after finishing this lecture. And you can visit the place, the kpop.org again by clicking this, or you can subscribe the YouTube K-pop channel by clicking that button. Okay. X21NQ, what is a wave? What is the wavelength lambda of psi t comma x equals a sine kx minus omega t? A wave is a function of time and spatial position. In one-dimensional wave is a function of time and x only, and in two-dimensional wave it will be x comma y. Or in the three-dimensional case, it is a function of time, x, y, and z. Okay, so therefore, this is a wave propagating along the x-axis. The wavelength is the minimum value of this value satisfying the periodicity. So if we substitute x plus lambda for the x, and we have the same quantity identical to the original wave. So in that case, that is the period in space. The period in space is called the wavelength, and the period in time space, that is called the period. So we use capital T for the period in time and use lambda for the period in space. We usually use the positive definite value for the period t and wavelength lambda. Why don't we substitute x plus lambda for the x? Then we find that this kx minus omega t is identical to each other, and this is a translation by k lambda. We expect these two are identical to each other only if k lambda is a 2 pi's multiple, 2 pi n, something like that, where n is an arbitrary integer. The minimum value for this is n is a plus 1. In that case, we have k lambda equals 2 pi. Therefore, the wavelength lambda is obtained as 2 pi over k. So here k is called the wave number. The wave number k is, by exchange lambda and k, we find k is 2 pi over lambda. What is the period t? In this case, we do the same job. Instead of replacing x, we replace t by t plus capital T. That is the period in time. So again, this omega t should be a multiple of 2 pi, and the minimum value is obtained by substituting n by 1. Therefore, the angular frequency omega is 2 pi over period capital T, and the period capital T is 2 pi over omega. Number 3. Describe how to determine the velocity of the propagation of wave. Okay. If a wave propagates along the x-axis with the velocity v, then at t equals 0, we have a certain wave. And as time goes by, it moves in such a manner. So, this distance of travel of the wave is v times t. And because the shape of this function is identical to the original one appeared at t equals 0. For example, psi t of x at evaluated at t equals 0 is a psi 0 comma x. Okay? So this guy translates by amount of vt at time t in comparison with at time t equals 0. So what we have to do is substitute x minus vt. Okay, so this is a function that has been translated from, this is a psi 0x, and this is a psi 0x minus vt that has been translated along the E1 direction by vt. So this is a way to describe the wave by making use of a distribution of the fluctuation of the wave at a certain fixed time. As a result, we can think about this distribution of a fluctuation in case x space only at a fixed time t equals 0. Now we require this translational relation at time t, so we substitute x minus vt for this x in the distribution at time t equals 0. We can expand this to find that we have kx minus omega t, where omega must satisfy the k times v. As a result, this velocity v is omega divided by k. We recall that the angular frequency omega is 2 pi over period. And wave number is 2 pi over wavelength. Because it is a reciprocal of the wave number, we multiply 2 pi over t by lambda over 2 pi. 2 pi cancels, and wavelength divided by the period is the speed of the propagation of this wave. We can extend this one to the three-dimensional wave, and in that case, we can choose the direction of propagation to be along the x-axis. So in general, the velocity has the magnitude and direction that is, in this case, along the x-axis and positive x-axis. Number 4, how can you determine the velocity of the propagation of a wave? Kx plus omega t. We remember that the propagation of a wave that is translating from certain point t equals 0 to t equals to t, and it is translated by Vt, that is the delta x. Okay, so at t equals 0, we used to have 0x, but it should be translated by plus Vt, so we substitute this one in this form. Previously, what we have obtained is x minus Vt, and expand this, and the result should be the same as this, as given above. Therefore, the velocity in here is, because this is a positive sign, velocity is the negative of omega over k. That means the propagation, direction of propagation is opposite. So wave vector is ke1 hat, and the magnitude of the wave number is k, that is a 2 pi over lambda, that is a positive definite. However, uh, and the frequency is also positive definite. However, the velocity of the propagation of this wave is opposite to the wave vector that is heading forward to the positive x-axis. Show that psi x comma t is fx minus vt, satisfy the equation, wave equation. This is called the wave equation that propagates along the x-axis with the speed v. Okay, so we define a function f of capital X. Now we replace this one, x minus vt, with the capital X substitution. If I take the derivative with respect to this capital X, we find it can be expressed as x prime, f prime of x. Double prime of x is the second order derivative with respect to this argument, capital X. Now capital X is actually x minus vt. We make use of chain rule to find that the partial derivative of capital X with respect to t is minus v. The partial derivative of capital X with respect to x is 1. All right. Therefore, we take the first order time derivative of f of capital X. We apply the chain rule to find that this one multiplied by the time derivative of x. We find that this time derivative of capital X is minus v. And as we have already stated, it is f prime of x. If I substitute x minus vt for this capital X, our final result is this. What happens if I take the double time derivative of f of capital X? First of all, the derivative is given in here, so why don't we copy this one in here? And v is a constant. This time derivative can be made again by using the chain rule. First, we take the derivative with respect to capital X, and then take the derivative of capital X with respect to small t time t. Again, we apply this to find that we have over a factor of a minus v squared, and the double derivative of f with respect to capital X. The final result is this. In a similar manner, what we can do for the x derivative is using this simple relation that capital X derivative is 1. So in here, minus v should be replaced with just a simple 1 unity, and v squared is to be replaced with 1. Therefore, if I divide this 1 by v squared, that is this that is identical to this. Therefore, if I subtract 1 over v squared, this subtracted by the double x derivative vanishes. So, this arbitrary function of f that whose argument is completely determined by x minus vt is satisfying the wave equation that is propagating along the either positive x-axis or negative x-axis. Finally, we arrive at the problem 6. Find the second order derivative of f of x with respect to x from the definition of the derivative. The first order derivative is normally defined like that, and it is a fourth derivative at x and x plus h, where h is a positive. If we can also find the derivative by varying this value less than x, so this is a backward. Again, we can also evaluate the derivative by varying this both sides by x plus 1/2 of h and x minus 1/2 of h. Either way, if the derivative is a continuous function, then we do not have any problem with these three cases. Sometimes there is a discontinuity of the derivative, so one should be careful. But in most cases in physics, there will be no problem except for the case just like the bouncing a ball against the hardware. The second order derivative with respect to x can be evaluated by recursive application of this. Why don't we use the central one? Then this first order derivative's difference and this ratio limit, this is the second order derivative. And we can make use of this definition and substitute that value for x plus 1/2 of h and x minus 1/2 of h. Then we can find that the result is copying this and substitute x plus 1/2 of h and subtract it by the same thing, but evaluate it at x minus 1/2 of h. If I simplify all these things, this guy is this, and this guy, it becomes this. And these two terms are found to be the same. So we have double factor, and x plus h appears in here, x minus h appears there. In the middle, it is just f of x. In a similar manner, we can use this or this method. In that case, the same limit can be obtained by using this that translates from x by h and h translates from x by minus h and minus h again. Okay, that's it for today. Thank you.